Okay, Jai Hind students. Myself Alok Kumar, and today we will cover two important topics from ADC. First is the calculation of contact potential for PN junction diode, and second is the calculation of depletion width in case of PN junction diode. So these two important topics we will cover, right? So first of all, we will start with the we can say normal construction of the PN junction diode, and we will see how we can represent the charge density, how we can represent the electric field distribution, and how we can represent the potential in case of PN junction, right? So through diagrams we will see this. So first of all, suppose this is the PN junction, right? And here this is the width of depletion region, right? Here we have P type material, we have N type material. Okay. So on this P side we will have negative ions, right? We will have negative ions in depletion region, and from N side we can have positive ions in N region, or depletion width of N region, right? So now we can represent the charge density, we can represent the electric field, and we can represent the potential graphically, right? So to represent the charge density, so here suppose this is charge density rho, and here on this side we have negative charge, and in the same amount we have positive charge on this side. So this is representing negative charge, or we can say Q minus, and it is your we can say positive charge due to positive ions, and we can say this is Q plus, and obviously this Q negative should be is equal to Q positive, right? So now we have a Poisson equation. So according to Poisson equation, we can write dE over dx, it should be is equal to rho upon epsilon. So here this E is representing the electric field, this is representing the electric field, right? This is nothing but electric field. Rho is the charge density, and epsilon is the permittivity of the material. This is the permittivity of the material, right? And we have written this equation using the Poisson's equation. This is nothing but Poisson equation. Okay. So using this relationship, we can draw the electric field also with respect to x. With respect to x, we can draw the electric field. So here, if I consider this is minus xp, here x is 0, and here x is equal to xn, right? So in this respect, I can draw the electric field like this. So here I have minus xp, here x is 0, here x is xn, and here we can see when x is equal to 0, the electric field will be maximum, right? So the maximum value of this electric field, suppose it is Em. Okay. So this is the way how we can represent the electric field, and in similar manner we can represent the potential also. With respect to x, we can represent the potential. So here at x is equal to xn, here x is equal to minus xp. So here at x is equal to xn, the potential will be Vn. Here at x is equal to 0, the potential will be 0, and at x is equal to minus xp, potential will be Vp, right? So now what is our aim? We want to find this barrier potential, that means we want to find out Vn minus Vp, and this is nothing but Vb, we can say, and Vb is called the barrier potential, or we can say contact potential. So we are interested to find out the value of this barrier potential, right? So calculation of barrier potential, how we can do this, right? So to start with, first of all we will see that what is the total current due to holes or due to electrons in a semiconductor, right? So if I take the total current due to holes, so I can write it as JPX, it will be is equal to Q Px mu P into Ex minus Q dP, derivative of dpx by dx, right? So in this equation, this is the we can say the total current due to holes, right? So in this equation, if I see, this is nothing but drift current due to holes, drift current due to holes, and this one is the diffusion current, diffusion current due to holes, right? Here Q is the charge and Px we can say the concentration of holes, mu P is the mobility, and Ex is the electric field in this drift current. In diffusion current, again Q is the charge, dP is the diffusion constant, it is the diffusion constant, right? And this derivative of this Px with respect to x, it is nothing but the concentration gradient. This term is the concentration gradient. Due to this concentration gradient, we are getting this diffusion current also. So this is nothing but concentration gradient. Okay, so this is the final equation, or we can say the total current due to holes in a semiconductor. At equilibrium we can say this current should be 0, there should be no current. So if I equate this with 0, so 0 is equal to Q into Px mu P into Ex minus Q dP dpx by dx. I can write this, or I can also write Q into Px into mu P into Ex is equal to Q dP, derivative of Px with respect to x. So here I can cancel this Q, right? And we can rearrange the terms. We can write it as mu P upon dP into Ex is equal to 1 upon Px and d Px upon dx. We can write this. Now we know the Einstein relation, and Einstein relation is dN upon mu n is equal to dP upon mu P is equal to kT upon Q. This is the Einstein relation. Okay, so from this relation we can find this mu P upon dP, mu P upon dP we can find the mu P upon dP, and it will be is equal to Q upon kT, Q upon kT. So I can write here, so this equation will be Q upon kT into Ex is equal to 1 upon Px, 1 upon Px derivative of Px with respect to x, right? Again this electric field can be written as minus dVx by dx. In terms of voltage we can write it as, so here we can write Q upon Qt into minus dVx by dx is equal to 1 upon Px dpx by dx, right? Or if I integrate this equation, so what I can write, we can write minus Q upon kT integration Vp to Vn dV is equal to integration 1 upon P dP, and this should be from PP to Pn, concentration of holes from P side to N side. Like this here, here we have put the limit, that is potential from P side to N side, Vp to Vn, that is potential at minus Xp is Vp and potential at Xn is Vn. So, we have applied the limits from Vp to Vn, and similarly here for concentration from P side to N side, what is the concentration of holes? So, we have applied the limits from Pp to Pn, right. After solving this, we will get minus q upon kT Vn minus Vp is equal to, this is nothing but we can say log base E Pn minus log base E Pp, right. Or it can be written as minus q upon kT, this is nothing but Vb or barrier potential, and it can be written as log base E Pn upon Pp, right. Or in after simplifying this, we can write Vb is equal to kT upon q log base E, and to absorb this minus sign, we can just inverse this relation. So, we can write Pp upon Pn. So, here I can write Pp upon Pn. So, this will be the expression for potential barrier, or we can say contact potential. Here Vb is the barrier potential, K is the Boltzmann constant, T is the temperature, and Q is the charge. Pp is the, we can say, the majority carrier concentration in P type, because we know the holes are the majority, holes are in majority in P type, and Pn represents the minority carrier concentration in N type, right, or we can say hole concentration in N type. This formula can be modified in other forms also. So, from law of mass action, as we know from law of mass action, we can write Nn into Pn is equal to Ni square. This is for N type semiconductors, and in N type semiconductors we know this Nn is nothing but it can be equal to approximately equal to Nd. So, Nd into Pn is equal to Ni square, and from here I can find the value of this Pn, it will be Ni square upon Nd, right. So, I can use this value and I will put this in this equation, right. Similarly, we can find this, we can replace this Pp can be replaced by, Na, right, the acceptor atoms concentration. So, this Vb can be written as Vb is equal to kT upon q into log base E, and here I can write Na into Nd upon Ni square. So, the another form of this contact potential or barrier potential will be this. So, here we have Na and D, product of Na and D. Na is the concentration of acceptor atoms, and D is the concentration of donor atoms, and Ni is the intrinsic carrier concentration, and again K is the Boltzmann constant and T is the temperature in Kelvin. So, using these values, if I put these values, I can find the barrier potential for any PN junction, right. Simply we can say for silicon, this Vb is approximately equal to 0.7 volt, and for germanium this Vb is 0.3 volt, right. So, this is the way how we can find the contact potential or barrier potential, right. So, next we will see the calculation of depletion width, how we can calculate the depletion width. Okay. So, depletion width of PN junction or calculation of depletion width. So, if I represent it with W, capital W, so calculation of depletion width, capital W, right. So, in PN junction we can see, in PN junction, if this is, or we can say the depletion layer, if this is our depletion layer, here we have this p type material, n type material, and here I have this value is minus xp, this is 0 and this is xn, and this complete is called w. So I can say w is nothing but xp plus xn. So if I calculate xp and xn, I can find the value of this w, right? So to start with, we will start with Poisson equation. So we know we have a relation, that is dE over dx is equal to rho upon epsilon, right? Or we can also say d square v over dx square is equal to minus rho upon epsilon. It is one another form of Poisson equation. So this is nothing but Poisson equation, right? Now this rho is the charge density. So if I found that, if I find the total charge in the PN junction, so what is the total charge? This rho should be is equal to q into, I have holes, I have in positive charge I have holes, I have acceptor atoms, in negative charge I have electrons, and I have sorry, I will write it again. So in positive charge I have holes and I have donor atoms, that is Nd, and similarly in negative charge I have electrons and I have acceptor atoms, that is Na. So this is the total charge, okay, or we can say total charge density. But we are talking, we are concentrating only about this depletion region, okay, or depletion layer. In depletion layer there is no charge carrier, there is no electron or hole available in the depletion region. We only have donor and acceptor atoms in the depletion region. So I can remove this p and n from this equation, and I can write it as q into Nd minus Na, right? So now this equation can be, I can rewrite this equation. So it will be dE over dx, and it will be is equal to q into Nd minus Na upon epsilon, right? Now for different value of x, I can further write this equation, or I can break this equation. So I can write dE over dx is equal to q into Nd upon epsilon for 0 to xn, right? For this range, I have the charge density will be q into Nd, and so dE over dx will be q into Nd upon epsilon. Again I can write dE over dx is equal to minus q into Na upon epsilon, and now the range is minus xp to 0. For this range, this formula can be written in this form, okay. Now if I integrate this, what I will get? I will get integration. So here limit is 0 to xn, okay, and in this limit how the electric field is changing? At x is equal to 0, electric field is Em, and at xn is equal to 0, electric field is 0. So if the limit for x is 0 to xn, then the limit for electric field will be Em to 0. So here I will write Em to 0 into dE is equal to q Nd upon epsilon integration 0 to xn and dx. I can write this, okay. After solving this, we will have so if we apply the limits, what we can write? It will be Em is equal to minus q into Nd upon epsilon into xn. After solving this, I will get this, okay. So EM is equal to minus Q and D upon epsilon into Xn. Now this EM again I can write in terms of V. Okay, so I have E is equal to dVx by dx, right? So I can write this. Okay. Before that, if I solve it for this equation, so here EM will be is equal to minus Q Na upon epsilon into xp, right? So if I equate these two equations, suppose this is equation number 1 and this one is equation number 2, and if I equate these equations, from here I will get Nd into Xn, it will be is equal to Na into xp. So I have to use this relationship in further steps, so please remember this. Okay, now in this equation number 1, if I take this equation number 1, what I can write? I can write dV over dx is equal to minus Q and D, minus dV over dx is equal to minus Q and D over epsilon into Xn. If I further integrate this, so I can have minus Vp to Vn dV is equal to minus Q and D upon epsilon in integration minus xp to xn and with respect to dx. Okay, so after solving this, we are taking the limits from 0 to xn. Okay, so here the limits will be different. Okay, so here the limits will be different. As we are taking from 0 to xn, so at x is equal to 0, v is 0, and at x is equal to xn, v is vn. So we will take the limit from 0 to vn, and similarly here we will take the limit from 0 to xn. Okay, after solving this, we will get Vn is equal to Q and D upon epsilon into Xn square by 2. Okay, similarly we can say Vp will be is equal to Q and D xp square upon epsilon by 2, right? So we will obtain this, and Vn minus Vp we know it is equal to Vb, and here it will be is equal to Q and D upon epsilon into Xn square by 2 and minus, so in this Vp we will obtain the minus sign, so minus Q, here it should be Na. Okay, it should be Na. It should be Na, right? So, and Q and D Xn square upon 2 epsilon minus Q Na xp square upon epsilon into 2. So we will obtain this. After simplifying this, we will have Vb is equal to, so what I can write, Q upon 2 epsilon I can take common. Okay, so Q upon 2 epsilon into Nd Xn square minus Na xp square, right? Now here it should be plus, minus plus, so here we should have plus sign. Okay, so I have proved that Nd, we can see in this equation, Nd into Xn is equal to Na into xp. So now we will use it, Nd into Xn is equal to Na into xp. So if I find the value of xp will be is equal to Nd Xn upon Na. I will use this, I will put this value in this equation. So Vb is equal to q upon 2 epsilon into nd xn square plus na, and in place of xp I can write nd square xn square divided by na square, right? So one power will get cancelled with this, and vb will be equal to q upon 2 epsilon, right? Now I can take common nd xn square, I can take common, and here I will get 1 plus nd upon na, right? Or further I will simplify it, q upon 2 epsilon into nd xn square. After solving this I can write na plus nd divided by na, right? From here I can find the value of xn square. Xn square will be is equal to 2 epsilon Vb upon q nd xn square. Here we will have Na, and here we have Na plus Nd, right? Or after simplifying this I can write xn is equal to 2 epsilon Vb upon q, 2 epsilon Vb upon q into Na upon Nd into Na plus Nd to the power 1 by 2. So this is the value of xn. Similarly we can calculate xp, and xp will be is equal to 2 epsilon Vb upon q into Nd upon Na into Na plus Nd to the power half, right? To the power half. So what will be the total depletion width? We have calculated xn, we have calculated xp. So what will be the total depletion width? W will be is equal to this xp plus xn, right? So put the value of xp and xn. We can have 2 epsilon Vb upon q, right, into Na plus Nd, right, to the power 1 by 2 into Na upon Nd to the power half plus Nd upon Na to the power half, right? After simplifying this we will have 2 epsilon Vb upon q into Na plus Nd to the power half into, here we will have Na plus Nd divided by Na Nd, right, Na Nd to the power half. Or after simplifying this we can write W will be 2 epsilon Vb upon q into Na plus Nd divided by Na Nd to the power half, or we can say under root of this. So the final value of depletion width will be W is equal to under root 2 epsilon VB upon Q, Na plus Nd upon Na into Nd. This will be the final expression for the depletion width, right? So thank you.